It's funny when people use pictures instead of themselves. It's kind of a confusing thing. Okay, so let's look at cellular respiration. That might help. I wonder if that's the issue. Okay, so like I said, I have not taught this forever. But when we're trying to get energy, the energy that we need is what? What form of energy? What's the energy that we use in our cells?
ATP.
ATP, okay? So this is showing you that we start out with things like sugars, right? Glucose, oxygen, and ADP. And what we end up with is through chemical reactions, we end up with CO2, water, and ATP. So what we're trying to do is take a sugar and generate energy. And when we do that, we take the sugar molecules that have high energy and we break them down and produce CO2. Yes? And water and also ATP. Okay? So this is what our cells are doing at the time. So they go through all these different steps. And what we end up with is as we break down sugars, we end up with CO2. Okay? And so why is that important that we produce CO2 from a physiological perspective?
Because CO2 combines with water to produce bicarbonate.
And so we end up with carbonic acid, right?
Okay.
And then we end up with bicarbonate ions and hydrogen ions. And we talked about that reaction, I feel like, a lot this quarter. And last quarter, too. So if we're generating a lot of CO2, we can end up with a lot of acid in there as well because of that particular reaction. So if your cells are trying to generate ATP for whatever process they need, they're going to take sugars or other energy sources. Usually we just start with sugars because it's easier to understand the chemistry of it. And we break down those sugars and we produce ATP and we produce CO2. So in your body, this is also happening. So if you, where were we? We were on this thing. So as you exercise, like what's going to happen? Your body is going to be using up energy, right? It's going to be taking sugars and breaking them down so that you can have ATP to power all those muscle contractions. Because remember that ATP is important for the cross-bridge detachment when we talked about muscle contraction, yes? So you need to be making ATP all the time. And as you go through that process, what you're doing is you are creating a slightly acidic environment. But so when you're also doing that, you're also generating a whole bunch of CO2, and you're using up oxygen because in those reactions, you're using up oxygen as part of the whole process. So if we know that the pH is low, we know that we need more oxygen to fuel these processes that are going on in our cells. And if we have elevated CO2 or a lower pH, that sort of gives us a clue that all of this is going on. And we need to be unloading more oxygen in the tissues. I don't know if that helped or didn't help.
It helped.
Yeah.
So this one, so this problem here is just having you look at the graph. This first problem is just having you interpret the graph. So it's just looking at a partial pressure of oxygen of 20 and having you compare the 7.2 line with the 7.4 line. And so you can come up with the percentages and subtract them. I don't think that is tricky. But the trickier ones, I think, were like this one, where you had to think about the DPG. So when you looked at the DPG one, let me see if I can, trying to move things so I can see. And you can see. Okay, when we looked at these graphs, remember, you had to try to figure out whether it's a good thing or a bad thing to have DPG. So what this says is that if you have low exposure to low levels of oxygen for extended periods of time, leads to an increase in 2,3-DPG production by red blood cells. And so this is sort of a clue. So like normally, when you have 2,3-DPG, your curve is shifted which way compared to without it?
The right.
To the right.
If you have some, it shifts which way?
To the right?
To the right. And what does that mean is going to happen when it shifts to the right?
More oxygen is being given to the tissues.
Yeah, that just means that more oxygen is being given to the tissues. So, so when it moves to the right, if we have a blood being stored, losing its content of normal content of 2,3-DPG, it shifts further it shifts to the left, right? So here's our normal curve. In a blood bank, it'll be shifted to the left. And then when they add it, it shifts to the right. So which way do you want to have it? Well, you want to have it shifted to the right because this allows your tissues to have oxygen delivered when there's low levels of oxygen. So without the DPG, you can see the curve is super steep.
Mm-hmm.
And so like even if you're at 20 millimeters of mercury, and where did we say that you would find 20 millimeters of mercury as a partial pressure of oxygen?
In like a resting cell?
40 was resting, so what's 20?
Oh, muscle.
Like something that's more active, right? And so in this case, if you're in like an active muscle cell and you're looking at 20 millimeters of mercury as the partial pressure of oxygen, and 60% of your oxygen is attached to hemoglobin, is that good?
Mm-mm.
No. Why is that not good?
Not being able to...
You're at a deficit. And
You're at a deficit, and so what do you need to do to your hemoglobin?
To unbind.
We want it to unbind, so we want to kick off all those little oxygen molecules and put them in the tissue so that they're available.
Right.
Does that make sense?
Yeah.
Other questions about this? Let me see what I had in what I had in the PowerPoint about it. I don't know if I had that much more. I think actually I didn't have it in my notes because maybe I added it later or something. Let's look at what I have in my notes. Let's see. Okay. Okay. Now I had some graphs in here somewhere. Oh, here they are. Okay. So the graphs that I showed you in class was just showing you that you compare the dissolved oxygen, which is very little, with the oxygen equilibrium curve. And this one is, so sometimes they have percent saturation on the y-axis. Sometimes they just have the total amount. And so that includes the dissolved oxygen too, but the dissolved oxygen is pretty much negligible. So this is one thing. And so I just wanted you to realize that there isn't very much dissolved oxygen. And then we looked at the Bohr effect. So the Bohr effect is just showing you that with elevated levels of CO2, which way does the curve shift?
To the right?
To the right. And why is that helpful?
Because it causes your hemoglobin to detach from the oxygen and like let it go to tissue.
So it causes more oxygen to detach and be delivered to the tissues. So that's the only other one I showed you in class. So yeah, if you have that basic idea, even if you don't feel super confident about it, if you understand the idea of shifting to the right, meaning that the vertical part is shifting to the right, then that would be a good thing.
Okay.
Other questions?
Can we go over counter-current multiplication?
Yes.
I don't know. I feel like the urinary stuff didn't really stick with me.
Yeah. But you were able to get the videos things, right?
Yes. Yeah. Thank you.
Okay. So let's go look at urinary. We went through it, I think, kind of quickly. And it's also via Zoom, which I like Zoom, but it's not quite the same, I don't think.
No.
But I think it's definitely better than just having a class, where I record. Okay, let's do this. All right. So let's talk about countercurrent multiplication. And with countercurrent multiplication, the whole idea is that we have things moving in the opposite direction. So when we create a filtrate, right? So we create a filtrate. So over here would be the glomerulus, yes? And so the blood, there's all those capillaries in the glomerulus. And we talked about the membrane, and they push a bunch of liquid through. And that liquid that we push through is the filtrate. And we talked about how with the filtrate, we'll be having a whole bunch of reabsorption and secretion at the proximal convoluted tubule. So at that point, we're going to be using active transport mechanisms and osmosis and passive transport mechanisms. We're using a whole bunch of mechanisms to move things out of the tubule, of the proximal convoluted tubule. So, for example, if we have glucose in the tubule, we're going to be using special glucose transporters to stick the glucose where? Where do we want the glucose to be? Do we want it in the urine?
No.
No, so we want it to go back into the blood. So at that point, we have a whole bunch of solutes leaving. But with those solutes, we'll also have a lot of what leaving? We'll have water following. So when we lose the solutes, we lose the water. And so the concentration of solutes, or the osmolarity of the solution, doesn't really change that much because we lose both solutes and water at that point. Then the filtrate continues on through the path. And are you guys comfortable with what happens in all the different sections of the nephron? Or not really?
Yeah, I think I just need to review it, but I understand it.
Yeah.
So in this case, what we're seeing is we're going down through the descending loop of Henle. And when we go down through the descending loop of Henle, what happens to the concentration of solutes in the tubule?
Increases?
They increase. And why do they increase?
Because water is leaving.
So because water is leaving, okay? And then we go back up, and then what happens to the concentration of solutes?
It goes back down because solutes are leaving.
Yeah, this time the solutes are leaving, and it's sodium, potassium, and chloride ions with this import protein.
Mm-hmm.
Okay, and then we keep traveling, and then we go back down through the collecting duct, and what happens to the urine?
It becomes more concentrated.
It becomes more concentrated. Okay, because, again, what will we have leaving at this point? Water. If we have aquaporins present, and that will be determined by the presence of ADH. So we have this whole process happening here, just like this. And as we do this, we can see that we have this typical pattern of solutes becoming more concentrated as it goes deeper, less concentrated, and more concentrated. So in order to sort of maintain this gradient, we have blood flowing which way? Does it flow the same direction as the filtrate, or does it flow in a different direction?
Opposite.
Different.
It flows in the opposite direction. So this helps to amplify the signal. And so this also helps us because when the fluid travels through the collecting duct, it will be surrounded by fluid that is going to be of higher concentration as it goes deeper. Because remember, this whole thing is just all crumpled up like that. It's all wrapped around each other.
Mm-hmm.
And so as you have everything all crumpled up, the collecting duct is in the same area as all these other things. And so it'll be bathed by fluid that will be increasing concentration as it goes more deeply. And then this will help you to form concentrated urine because of the surrounding fluid concentration. Well, in order to help the surrounding fluid to maintain that high concentration, we have blood flowing in the opposite direction of the urine. So here, this is showing you blood concentration. So it starts out at 300, similar to what's in the collecting duct at this level. So it goes down, and then what happens here to the concentration of solutes in the blood?
It gets higher.
It gets higher. Why does it get higher?
Because ions are moving into
Ions
the
are
blood.
moving in. So if they're going out of the filtrate, they're going into the blood. So it gets more concentrated and more concentrated and more concentrated. And then what happens over here, though? What starts moving in there?
Water.
Water.
Water. So we have the opposite thing happening. And what happens then? Becomes less concentrated. So we have these two loops
Okay.
running in opposite directions. And when things go out of one loop, they go into the other loop. And so if we have ions leaving the filtrate, they're going to go into the blood. And if we have water leaving the filtrate, it'll go into the blood. And the water will want to go in the blood. Why will the water be driven into the blood?
It's a high solute concentration.
Yeah, there's a high solute concentration. So this just sort of amplifies the effect. And so this is just allows us to form highly concentrated urine because we end up with this lovely gradient where it becomes more concentrated the deeper that you are into the nephron.
Okay.
Okay?
Yeah, that makes sense.
So one thing we talked about was